Hello, good morning. Welcome to this new class. This this class on diesel engine repairs, which is part of the specialization on heavy mechanics of heavy trucks. My name is Cesar Cárdenas. I'm the professor, teacher responsible for this class. And today we're gonna start with our first class, our first session on this topic, on these issues, which is very interesting. Today, we're gonna go over some study case, which is about a diesel of the crankshaft bearings failures or fails that can be found on these components that are part of the diesel engine. So the crankshaft bearings, have different types of damages, right? And this study case, the one that I wanted to talk today about, is about some different covers actually some different types of damages, right? And from two different perspectives. Let's say from the material, that are of these components are made of some different materials. So the materials used, to manufacture these bearings, this is one of the perspectives, and the other one is about the position of the bearings within the crankshaft. So this is as I said, a very interesting case. We're gonna start just by showing you the bearing positions on the crankshaft. The idea here is of this study case, which is a study that is a research work. Actually, this is part of a paper, right? A research work that was done recently, yes, it's about just a couple of years ago, by a faculty of mechanical engineering in Europe, in a university in Europe. So they found very interesting damages here, depending on the position of the bearings. So here we have an oil hole. All of you are already familiarized with this piece. This is a crankshaft, but of a diesel engine, right? So we have here connecting rod bearings here, and the main bearings. So this is the position of the bearings that have been studied here. And from, as I said before, from two different perspectives. The first one is the position. What happens if you, with the damages or the wear of a bearing that is located here, for example, and what happens, what are the kind of damages, or how it can wear, these bearings can wear if they are located here. So there are comparative study here between the position of the bearings here and the damages that can be found here and the damages that can be here, depending on the positions of the bearings. So there are bearings studied in this position, bearings are studied here when are here in this position. So that was a bearing position on the crankshaft. So the crankshaft, as I said, that all of you are familiarized with this piece, but the main topic of the idea of this study is to just show the comparative study between those bearings, the bearings that are located in these two different positions, right? So the wear, keep in mind that this is kind of tribological study that involves tribological studies. So whereas tribological process has a major influence on the reliability and life of the engine crankshaft bearings. So the importance of this examination of bearing fails or failures due to wear is very well known. This is very well known. But the point to the possible causes of wear and to the necessary treatment for its reduction of elimination. So there are in this paper, or in this case study, there are some pictures that I want to show you later on a different slide. That shows, for example, some kind of heat treatment, that is applied to these kind of pieces, to bearings, right? And how the type of damages when there is a heat treatment and stuff like that, when there is not some kind of thing. So there is a very comparative study, as I said, is kind of interesting. So this paper, as I said, present this kind of results. So that I studied that are obtained, or that were obtained by examining 660 crankshaft bearings. Imagine that. So 616 crankshaft bearings were studied. So 16, over than 600 pieces, of crankshaft bearings that were damaged actually by different mechanisms. And the bearings, as I said, were installed in high-speed diesel engines, and were gathered for 2 years. So they were there for 2 years and doing different general repairs of the engines, what is called in English, or what is known in English as an overhaul process. So after between 30,000 and 50,000 working hours, so after the examination of the bearings, so a fault tree analysis was done, performed to determine the root causes for the engine bearings failures. So it's very interesting, this study. So each type of damage was identified and illustrated with high resolution photos. I might show you some of them later on this on different slides. So that's these here are the bearing types and materials that were used. So as I said before, we have 1616 total number of bearings that were studied, so more over than 16 bearings that were located located on main crankshaft bearings. 342 out of 1616 were located here on the main crankshaft bearings, and the others 274 out of these 616 bearings were located on connecting rod bearings, as I showed you before in the first picture photo that we saw. And 342 were made of these, or composed of these materials, from 210 and 132 of these kind of materials, right? And the connecting bearings, 274 as I said, and 19 of them were composed of these materials, and 178% were manufactured with these materials, right? So this is the materials and the number of bearings of the total of them that were manufactured and were checked, and examined after 3,000, 5,000 hours of operation in a diesel engine or high-speed diesel engine. And this is the different types of damages, or let's say wears that can be, or that were studied, or the type of damages that were studied here. Remember that the reliability of diesel engines and other machinery is a function of the faultlessness of its moving parts. And in this case, bearings are certainly among the most important elements of a diesel engine. So here we have some kind of field examination details that are shown here in this chart. So we have in this graphic we have different damages. So here we have abrasive wear, adhesive wear right here, surface fatigue wear, cavitation wear, corrosive wear, erosive wear, plastic deformation, and fracture. So remember that we have this it's more related to strength of materials. We have a curve there, and when any material gets this plastic deformation, plastic area, it fractures, So it's something similar to that. So we have here that the frequency in percentage, 60%, and the type of damage. So look at here that for abrasive wear, 59.4%, of this damage was related to abrasive wear. 18.9 related to adhesive wear. 11.1% surface fatigue wear. Cavitation 6.8, and the others. Right? Those were the types of damages. 60% of them. So remember that the study says. This study case says that after 4,000, 5,000, or between 4,000 and 5,000 hours of operation, these bearings were examined again, let's say were installed, put on a high-speed diesel engine, and after overhaul process, after a general repairs and overhauling, these were examined again to check, the type of the damages that were that maybe can come up with these kind of components. Right. Then here I show those are the pictures that I mentioned before. So you have the majority here as we saw in the previous slide, the majority of the damages were due to abrasive wear. And these damages that's what the study case says, are manifested by scratches, from very fine to clearly visible scratches. So we have here, for example, those scratches, right? We can see some of those here. So, and we have the abrasive here. This is abrasive, abrasive wear, some kind of abrasive wear. And in B we have the detail of a bearing in the middle, alloy. This is, remember the alloys. I'm gonna go back here very real quick, right here to this alloy right here. This is an alloy, right? That was used on this kind of component, this bearing, and this is some kind of radiography, something like that, or scan, and it shows here a detail bearing in the middle, in the middle with this alloy. So we have here abrasive wear, adhesive wear here. This is another kind of, this is all after all those thousands of hours of operation. They were taken out, apart, or taken out from the engine and examined, to check the kind of wear that were, found there, or that can be found there. And here we have surface wear and corrosive wear. So those of these pictures, show those kind of the wears that were found during this study. And what else we have here? Bearing surfaces damaged by abrasive wear. We have that here. This is with the alloy, right? And for example, this surface wear, fatigue or surface fatigue wear, was present only at an initial stage, and was shown or manifested with fatigue cracks, right? Fatigue cracks. This is some kind of being here, fatigue which stem from the sliding surface in the lower zone propagating as a network, and there were no characteristic places where cracks occur, and there were no bound faults, or something that is called the detachment of lining of material. I'm not sure if you're are familiarized with that kind of term, but it's very common, for example, when you work with composite materials, that you can find some kind of detachment of lining material. So that is a kind of important damage. Right, the cavitation wear is seen predominantly in diesel engine bearings, but two types of cavitation wear in this study were noticed: the flow cavitation and discharge cavitation. Right. If you want more information on this, I can email you the study case, which is a paper, can be very interesting, that was done or performed a couple of years ago. In the case of corrosive wear, as the example that we have here, it was noticed only on the on this kind. I'm gonna go back. I'm not used to doing this, but here, it was the alloy that were used in this case, and it shows here the picture, that with the damage, so that was corrosive. That was only noticed on that kind of alloy, the one that I just showed you, and were very mild, not so big deal, but there was no direct contact with water, for example, and formation of oxide films was not noticed, was not observed. Right. So this is pretty much a brief, quick summary of these pictures, and the findings that were noticed, here during this study. Then we have something that is really, really interesting. Remember that normally we have in engineering with machines, and when you work with maintenance or something like that, industrial maintenance and stuff. There are talk about different kind of ways of, for example, in maintenance stuff, industrial maintenance of machinery. We can have different options to determine or establish the reliability and availability of equipment, something like that, by using, for example, a fault tree. Here in this case, we have, or in this study case, a fault tree analysis also was used or was applied. So the possible causes of a diesel engine crash have bearing failure or bearing fault, which was detected during this kind of research and investigation are used for the fault tree analysis, which is known as a FTA analysis, right? So the different types of bearings damages were correlated with a standard. There are more details in the paper, which can be useful for the explanation, description of the way the fault true analysis were designed and the root causes. If there's something important issue that the constructor fault tree analysis here for this electrical charge bearing failure can be useful by engineers in practice. You can apply this kind of fault tree analysis and use it. So remember that fault tree analysis, if we have a gate, it could be an and or gate, right? So, but you want information, you can get information or anything about all this fault tree analysis and stuff like that. But the idea here is to show you that we have a crankshaft bearing failure, which could be tribological and or mechanical failure, right? Tribological, remember that involves friction, wear, lubrication and stuff like that, or mechanical failure, right? So here we're going to go more in detail. So we have the tribological failure fault tree analysis right here, and the mechanical failure, tree analysis here. So in the case of the mechanical failure, it was mentioned before, the plastic deformation, or you can have insufficient oil supply, or low cost, or both, on, or and. So depending on the, this kind of, let's say this is called gate, right? That could be on and or. Remember the Boolean algebra and stuff like that. So you wanna check that and try to understand better this fault tree analysis. That would be very nice, but this is pretty much the way fault tree analysis is elaborated or designed or constructed, right? So you have this kind of fault tree analysis that show the condition that can be found, the condition that you can get, right, in these cases. So you can have different options here, for example, in fracture, over low impact loads and poor bonding, right? And here in the kind of tribological failure is a much bigger fault tree. You have more events and stuff like that. You have oil contamination, for example, for abrasive wear, oil contamination with wear products, a dust environment, poor filtration, and poor filtration as well here. So for fleeting wear, you have conditions here. For corrosive wear, condition. For erosive wear, you have condition, and all those are related with low frequency bearing rotation. Those involve tribology stuff here. For example, the adhesive wear, we have insufficient clearance, oil being breakdown, low oil viscosity, insufficient oil supply, right? Or to have here vibrations, overload, fault assembly, and poor design. That is common here. Find this kind of maybe poor designs and stuff like that that can cause any kind of fault. And the cavitation, where you have incorrect fluid flow, oil pressure fluctuation, crankshaft vibrations, insufficient hardness of oil lining material, and improper design, and interrupted oil flow and stuff like that. So this is the way you can go through all these fault tree analysis, right? And to determine which condition, which events you can get. You have some of them, or one of those. Which conditions or events you can have, and or, right? Depending on the gate that is involved in the design of those fault trees. So here also, of course, we have some results that were obtained from this, right? I wanted to call your attention to this fault tree, because remember that we have some gates, that are used to elaborate this. But look at the way or the form, the shape, of these gates, right? That are so what I mean is, in the mechanical failure, after mentioning some of those events or conditions, you have plastic deformation, you have insufficient oil supply, or low viscosity or lubrication system failure, right? Because this is the gate that we have. Mechanical failure, you have a plastic deformation or fracture. Here, fracture over low impact loads or poor bonding, right? Because you have this kind of gate. So keep in mind that, because if we had here different gate, So the the way to understand or to analyze the fault tree will be different. And here, for example, I will just focus on, for example, abrasive wear. That is, you have tribological failure, you have abrasive wear, but you have oil contamination with foreign particles, or a density environment, or poor filtration. We have oil contaminated, oil contamination, with wear products, or poor filtration. Right? You have abrasive wear, oil contamination with foreign particles, or oil contamination with wear products. And for example, here in corrosive wear, we have improper material selection or thermal degradation of oil, right? So this is the way you can read and check this, analyze this fault tree analysis, which is very, very interesting. We have two different types of, and there are others, with gates. So now regarding some of the results and the discussion here, we have, look at here, the kind of interesting result. We have two different graphs, right? One is the connecting rod bearings right here. Percentage share is 50%, and main crankshaft bearings here 50%. So a total of 100% was abrasive wear. Abrasive wear. 58.5% adhesive wear, and 41.5% was about main crankshaft bearings in the case of adhesive wear. So 58% of them were placed in the connecting rod bearings, remember the position, and 41.5% of those bearings were in the main crash bearings, were located there, right, and had this kind of damage or wear type adhesive. And here we have the others. For example, here, that is cavity, 83.9% were located in the main crash shaft, right, bearings position, and 61.1% were located in the connecting rod, or part of the connecting rod bearings, and they have a cavity wear. So this is the way you can analyze this, analyze the results here. And here we have with the alloys. Remember the alloys that we checked before. So for example, 58.2% of those had abrasive wear, and 51.8% had this kind of alloy and had this kind of damage or wear type, right? So for example, the abrasive wear was 50%, 51%, 52% pretty much had this kind of alloy, right? And were treated with this kind of alloy, something like that, and had this kind of abrasive or this wear type. So on the same with the others. You want to analyze, for example, right here, you have cavitation, right? So 89%, almost pretty much 90% of those had this kind of alloy, right? And just 10% had this kind of alloy and were related to this kind of damage. So this is pretty much the results that were found here in this study case. So as you see, it's very, very kind of interesting, those kind of this kind of a study case. And if you want more information about all this information, about these results, just let me know, and I can email you this study case, which is a paper, and of course you can get even more information about details regarding this study case. So thanks for your attention, and I'll see you on the next video class, and have a good day.